All right, the clock is ticking, the exam is just hours away. So this is it, your super condensed final revision for electric charges and fields. We're cutting out on the noise and just focusing on locking in those essential concepts, the ones that connect what you know to the marks you're going to get. This isn't about learning anything new, it's all about rapid recall. So what's our mission here? It's simple. We're going to laser focus on the 20% of this chapter that, believe it or not, delivers about 80% of the marks. Yeah, I'm talking about the high-impact derivations, the formulas you absolutely have to know, and, of course, the classic traps that examiners love to set year after year. Let's jump right in. Okay, first things first, let's get inside the head of the person who's actually going to be marking your paper. See, this isn't just a physics exam, it's also about giving them the information in the exact way they've been trained to look for it. Understanding this is probably the biggest advantage you can have right now. Now, have a look at this. This isn't a guess. This is hard data from past papers. They have a massive focus on derivations. An incredible 85% of papers feature dipole field derivations, and 78% have something to do with Gauss's law. The message here is loud and clear. Mastering derivations isn't just a nice to have, it's the main event. This is where the big marks are waiting for you. And this right here, this illustrates the other side of the coin. It's not just about getting the right answer, it's about how you present it. Examiners are human, right? They reward work that's clear and easy to follow. A neat, labeled diagram isn't just for you. It's a huge signal to them that you're confident. On the flip side, tiny things like sign errors or forgetting your units, that's the fastest way to lose marks you totally deserve. Don't give them away. Okay, so let's build on that and get into the core content. We're going to target the absolute highest yield topics, the stuff that just keeps showing up relentlessly year after year. If you can nail these concepts, your foundation is going to be rock solid. First up, the electric dipole, and specifically the field on the axial line when that dipole is short. This formula is an absolute superstar. You'll see it in theory questions, you'll see it in derivations, and you'll definitely see it in numerical problems. You just have to know this one cold. So here's the crucial part. If you're under pressure in the exam and your mind goes blank, just remember this one phrase, 2p over r cubed. Why is this so important? Because a normal point charge has a field that drops off as r squared. A dipole field drops off way faster, as r cubed. That little difference is a favorite for multiple choice questions. And here is the trap. This is the one that catches so many students, even the really good ones. Your muscle memory from working with Coulomb's law is screaming r squared at you. For a dipole, you have to consciously ignore that instinct. Make it habit before you finish any dipole problem, physically point your pen at that exponent and double check that it's a 3. All right, next up is the most powerful shortcut in all of electrostatics, Gauss's law. What does it mean in plain English? Just that the total electric flux punching out of any closed surface is directly proportional to the total charge that you've trapped inside it. For any problem that has some kind of symmetry, this law is your best friend. You see, I've put that word in all caps. There's a reason for that. Everything, and I mean everything, about Gauss's law hinges on that one single word, enclosed. It's not about the charges outside or the ones nearby or anywhere else. It is only and always about the net charge you have managed to trap inside your imaginary surface. And of course, this is the classic exam trap. They'll draw you a nice little picture with 5 different charges, but your imaginary Gaussian surface only has 2 of them inside it. They are literally testing you to see if you know to ignore the other 3. And yes, you do. Only the enclosed charge, Q enclosed, makes it into the right side of that equation. Okay, you've got the core ideas down. Now let's lock them into a completely foolproof structure for a 5-mark derivation. Remember that 85% statistic we saw for dipoles? This is how you confidently walk in and claim every single one of those marks. Here it is, your 4-step recipe for the axial dipole derivation. 1. A clean, fully labeled diagram. This is absolutely non-negotiable. 2. Write down the separate field expressions for the positive charge and the negative charge. 3. Add them up like vectors, which in this case means you'll be subtracting, and then just do the algebra. And 4, apply that binomial approximation for when r is much bigger than a to get to your final famous result. It's a template. Follow it every time. Now, for any Gauss's law derivation, your very first move pretty much decides the whole game. You have to choose a Gaussian surface that perfectly matches the symmetry of the charge distribution. If you see an infinite wire, your brain should immediately think cylinder. An infinite sheet? That needs a little cylindrical pillbox. A sphere?
Well, that needs another, bigger sphere. And the magic phrase you have to write down to unlock those marks is, by symmetry, the electric field is.
So now, let's assemble all these pieces into a game plan. Think of this as your rapid decision-making framework for that moment you first read a question in the exam hall, so you can instantly figure out which tool you need to solve it.
This matrix is basically your cheat code for identifying problems. You just have to read the question for the keywords. As soon as you see infinite line or infinite sheet, your brain has to immediately fire up Gauss's law. If you see charges set up in a geometric shape, like a square or a triangle, that's a superposition problem. Get ready to do some vector addition. And if you see any hint about a relationship with r cubed, you know it's a dipole. Let the question tell you exactly how to solve it. We are in the home stretch now. Let's pull all of this strategy together into one final, high-probability checklist that you can just run through in your head right before you walk into that exam hall. Okay, based on years and years of data, this right here is your highest probability list. Be ready to derive the field for an infinite line of charge. Be absolutely prepared to execute that four-step axial dipole derivation we just talked about. Know the formula for torque on a dipole, and know the conditions for stable versus unstable equilibrium. And you can almost guarantee you'll get at least one numerical problem on superposition. If you have these 5 areas locked down, you are walking in ready for whatever they throw at you. And just one final piece of advice. If you're ever in the exam and you feel stuck, if your mind just goes blank, stop trying to think and start drawing. A clean, well-labeled diagram is the single best way to clear your head and see the next step. It's really the physics version of pulling over to check the map. You have done the work. You have the strategy. Now go in there and get the marks you deserve. You've got this.